This is 5.1 exponential functions. The exponential function is f of x equals a to the x, where the exponential function with base a is defined for all real numbers x, and a has to be greater than 0 and not equal to 1. For the basic function of f of x equals a to the x, the domain is all real numbers. The range is y is greater than 0, because no matter how small the value of x gets, the value of f of x will never reach 0, which means the horizontal asymptote is y equals 0. So let's look at graphing. Here we have an example. We have f of x equals 2 to the x. And what we're going to do is we're going to plug in the standard values of -2, -1, 0, 1, and 2. So we want to use these standard values. Okay? And so when we plug that in, we think, okay, what is 2 to the -2? Well, we know that 2 squared equals 4. And what the negative does is it creates the reciprocal value of the 4. So it's really 1 over 2 squared, which is 1/4. Okay? So you know that 2 squared is 4, so 2 to the -2 is 1/4. Same thing with 2 to the -1. It's really just 1 over 2 to the first, so 1/2. 0, any number to the 0 power is 1. 2 to the first is 2, and 2 squared is 4. Okay, so now we just plot these points on the graph, and I didn't give myself a very good graph here. But anyway, let's look at this. This will be -1, -2, and -2 is 1/4, which is about right 1/4 of the way to 1, so that's a point right about right there. -1 will be 1/2, so that's not much higher. 0, 1, 1, 2, and 2, 4. Okay? Can you see how it's curving up? And if I really wanted to plot another point, I could plot 3, and 2 to the third is 8. Okay, so 3, 2, 1, 2, 3, 4, that's 2, 8. And you can see it's getting the distance between the points, and the vertical distance is getting greater and greater as we move over by 1 on the x value. So this is going to be, these are going to be hard to draw on slates here, okay? But that worked out pretty well. So it's going to be this curve. It's called an exponential growth, okay? And the domain of this would be all real numbers. The range is y is greater than 0, and the horizontal asymptote, HA, is y equals 0. As you can see, this line is going to get closer and closer and closer. It's going to ride right along the x-axis. So y equals 0 is your horizontal asymptote. You're not limited on any values of x being plugged into the function, and so the domain would be range, and your y values don't go below the x-axis. They stay above, and you can see they're going to go to positive infinity. So y is greater than 0. Okay, something you should notice here when you're graphing exponential functions and creating this value, the 2 and the -2 create reciprocals of each other. So 4 and 1/4. The 1 and the -1 are reciprocals of each other. And 0 gives you a value of 1, because any number with the exponent of 0 is going to equal 1. Okay? And so the y-intercept basically is always going to be 1. Now let's look at this example with a fraction, 1/3 x, 1/3 to the x. Okay, so we're going to put in -2, so we have 1/3 to the -2. Now just like on the problem above, it's going to take the problem above, it took that 2 and made it into a fraction of 1/2 with the exponent. So with this problem here, it's going to be taking 1/3 and flipping that to be 3, because the reciprocal of 1/3 is 3, and now the exponent is +2, and 3 squared is 9. So 1/3 to the -1 is going to flip that fraction into be a 3 with an exponent of +1, which is 3. 1/3 to the 0 power, as I said before, anything to the 0 power is 1. 1/3 to the first power is just 1/3. And 1/3 to the second power, you take 1 squared over 3 squared, and you get 1 over 9. Okay? Again, -2 and +2 are reciprocals of each other. The -1 and the +1 gave us reciprocals of each other, 1/3 and 3. Okay? So let's go over to -2, and we have 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. -1 is going to give me 3, 0, 1, 1 and 1/3, 1 and 1/9. So you're just going to be plotting that point just barely above the x-axis. So, and then really if you try to keep going, you're just going to try to be, it's going to look like your points are on the x-axis, but in all reality, they're just getting really, really, really close. So here is my graph, and it's not quite. That's all right. And so that's going to be the graph. And see if I can move it over a little bit to actually be on the dots. There we go. Didn't mean to move the graph. Okay, so that's what the graph is going to look. And you can see that this is going from left to right, is going down, where the graph above was going up. So the graph going up was exponential growth. The graph that's going down like this is called exponential decay. And my domain is all real numbers. My range is still y is greater than 0. And my horizontal asymptote is still y equals 0. All right, so let's look at the next page here. We're going to now look at the natural exponential function. The natural exponential function is f of x equals e to the x. E is described as that value. E is described as the value that the function y equals 1 plus 1 over n with the exponent of n approaches as n is approaching infinity. So if we were to calculate 1 plus 1 over 100, 1 plus, I should put 1 plus 1 over 100 to the 100th. Okay, that's going to give us some answer, I have no idea, somewhere around 2.7. And if we do 1 plus 1 over a million, that's going to give us an answer closer to 7.177. And that has to be to the exponent of a million. Okay, and if the higher we get with that number under here, if we put a billion down there, oops, so the billion, okay, that's going to give you 2.718, et cetera, et cetera. And so the higher that value of n is getting, the closer and closer and closer we are getting to this value of e, which is approximately 2.71828. Okay, now I didn't calculate this function here. I know it's just going to be close to 2.7. And the value of e is basically the same thing as like thinking about the value of pi. Pi has a value assigned to it, like 3.1415. So does e. E has a value assigned to it. It is 2.71828, and it goes on forever and ever, just like pi does. Both are irrational numbers. All right. So e, the value of e is approaching 2.71828 as n is approaching infinity. So let's look at example using f of x equals 2 times e to the x. Well, first of all, since e is a value that is like pi, it is actually on your calculator. E to the x is on your calculator. On a graphing calculator, you have to do the second function and then the ln button. And the ln button is right next to the 4. So if you look at, your number pad is right here, and here's the 4. ln is just to the left of the 4. Okay? So you're going to use the second function and the ln. Let me just erase this part. So basically, we're just going to do 2 times e to the negative 2 using your calculator. And you're going to round this to 2 decimal places, and you'll get 0.27. You can't create a fraction out of it. When we do 2 times e to the negative 1, we will get 0.36. 2 times e to the 0, well, anything to the 0 power, even e, is going to be 1. So 2 times 1 is 2. 2 times e to the first is going to be 5.44. And 2 times e to the second is 14.78. So when I go to graph this, I am obviously going to be estimating. So negative 2 is around, 1/4. Negative 1 is around 1/3. 0, 2, 1, around 5.5. So 2, 3, 4, 5.5. And 3 is way up here at 14 and 3, almost 14 and 3/4. So 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It's going to be up here somewhere, okay, approximately. So again, you can see this curve. And this is extremely hard to graph with this tablet. Okay, so that's essentially what the graph will look like. And you can see this curve got more pronounced. It's going to be a little more steep than the original problem we did. Our domain is still all real numbers. Our range is still y is greater than 0. Our horizontal asymptote is still y equals 0, even though we multiplied by 2. Now let's look at how to find the equation of a graph when the graph is provided. Here's an example. I have this graph drawn out, and I labeled these points. I have 1, 4, and 2, 16. So I have my x's and y values. The basic function of an exponential function is y equals a to the x. So we can plug in our values of x and y. Well, if I choose the first point, 1, 4, I plug in my 4, and I get 4 equals a to the first. Well, a to the first is the same thing as a, so 4 is equal to a. And now I can write my exponential function y equals 4 to the x. I could have also taken the 2 and the 16. So if I would have put in y equals 16, so 16 equals a squared, and I'm trying to solve this for a. Well, to get a by itself, I had to take the square root, and I would get a equals 2, 4. Yep, the square root of 16 is 4, not 2. And again, I would see that my function would now be y equals 4 to the x. So not too hard. You just need to know what to look for. Every time, if your point here goes through 0, 1, you can look at that first point, 1, 4, and basically know that your a value is going to be 4, or whatever the y value is. Okay, now we're going to look at graphing using transformations. We have y equals a to the x minus h plus the k. So the exponent is the x minus h. And then outside of the exponent, we are adding k. Well, the h value moves the graph left or right in the opposite direction of the operation. The k value moves the graph up or down in the same direction of the operation. So let's clarify that a little bit. If this was a to the x plus 2, that would be left 2 units. If it was a to the x minus 2 up there, that would be to the right 2 units. And for the k value, if we had a to the x and then plus 3, that would be up 3. If we had a to the x and then minus the 3, that would be down 3. Okay? If there's a negative symbol out in the front of a, like y equals negative a to the x, that is going to reflect the graph vertically. If the negative is up in the exponent in front of the x, then the graph will reflect horizontally. And whenever we have values being added and subtracted like this with the h and the k, our domain stays all real numbers, but our range is going to be y is greater than the k. Okay? In our original function, we were adding nothing here, so we just had y is greater than 0. But since we're going to be adding, it's going to be moving our graph up and down, we have to adjust our range accordingly. So y is greater than k. And then our horizontal asymptote will also be changed to be y equals k. So let's look at graphing this example. F of x equals 2 to the x minus 3 plus 1. So the basic function is going to be 2 to the x. And we're going to start with that. And we're going to transform the basic function using our understanding of transformations. So from this equation, we know that this is going to be moving to the right by 3 units and up by 1. So first I'm going to start with my basic function of 2 to the x. I could take negative 2 and 1/4. I will graph this in blue. And I'm just going to graph the points. Negative 1 and 1/2, 0, 1, 1, 2, and 2, 4. Now I will graph our new function of 2 to the x minus 3 plus 1 in red. So I'm going to shift all these points to the right by 3 units and then up 1. So right by 3 units and up 1. Move to the right 3 units and up 1. Right by 3 units and up 1. Right by 3 units and up 1. And then same thing. Okay? So you can see the horizontal asymptote. I will graph this in red. Nope, it's not going to do what I want. I want this over here. Okay, sorry. So dashed line in red. There we go. So that would be our horizontal asymptote, because you can see this graph is getting closer and closer to 1 now. Okay? And so I will take my pen and graph. And there's the graph of the function 2 to the x minus 3 plus 1. Okay? So one way to look at this also is to think about your 1 there, your horizontal asymptote, and the fact that we're moving to the right 3 units. So we can move, we can kind of visually or mentally move our standard origin of the 2 to the x over 3 units, 1, 2, 3, and up 1, and base everything off of this. So if I think about this, if my focal point, instead of being the origin, is now 3, 1, here's my, I go up 1 unit, just like the graph over here went up 1 unit, and then if I move over 1, I went up 2 units. If I move over 2, I go up 4 units. So if I kind of adjust my focal point according to the shifting over 3 and up 1, I can have that same, if I just move over from that new focal point by our new x values, if I go left 2 units, I'm up a fourth. If I go left 1 unit, I'm up a half. If I stay at the focal point, I go up 1. Move right by 1 unit, I'm up 2. Move right 2 units, I'm up 4. So a couple ways to think about how to transform functions. Now let's look at 3 to the x minus 1. I'm going to take the basic function, 3 to the x. These are my points. If I plot those in the blue here, negative 2 and 1/9, negative 1 and 1/3, 0, 1, 1, 3, and 2, 9. Okay? And go to the red to graph the function. I am moving to the left by 2 units and down 1. So left 2 and down 1, left 2, down 1, left 2, down 1, left 2 and down 1, assuming this is our value, and left 2 and down 1. So you can see, if I were to draw my horizontal asymptote down here, you're getting closer and closer and closer to negative 1. So my domain is all real numbers. My range is y is greater than negative 1, and my horizontal asymptote is y equals negative 1, our k value. I didn't do the domain, range, and horizontal asymptote on the last problem, but it's just that k value. Okay? And there's our transformation. And again, if you wanted to shift to the left 2 units and down 1 and change your focal point to be that point down there, you could then kind of apply these movements from that focal point. So left 2 units, up a ninth, left 1 unit, up a third, left to right 0, and up 1, over 1, up 3, over 2, and up 9. Okay? Now, taking negative 3 to the x. Negative 3 out in front is reflecting this graph vertically. So again, I will graph in blue the original function. So negative 2 and 1/9, this is the original function is the same as the last one. So let me graph these points, 2 and then 3, 6, 9. So what I'm going to do is just reflect these across the x-axis. Okay? So instead of being positive 1/9, I'm going to be negative 1/9, negative 1/3, negative 1, negative 3, and negative 9. So right here, right there, right there, there, and there. Okay, and this is obviously coming up like this through my points. Okay, so just assume that went through there. Okay, so that's the reflection. Now, when you have a reflection, my domain is not going to be greater, or my domain is still all real numbers, but my range is not greater than 0 anymore. It's less than 0. So I have to adjust my thinking on that for my range, because my range is now going down instead of up. But my horizontal asymptote, in this case, will stay y equals 0. Okay? And that's what we want to do when we graph with transformations. And that does it, I believe. Let me look here, see if I have another page. Nope. Yep, that does it for 5.1.